After the separation of the molecules, we need a tool to identify and quantify those molecules. And we'll see the case of mass spectrometry. So first of all, what is mass spectrometry and how does it work? Well, it's an analytical technique aiming at identifying and quantifying molecules by measuring their mass. What is the mass of a molecule? Well, this is the sum of the mass of the atoms composing this molecule. Here you have the case of rutin, which is a phenolic compound conjugated with sugars. And the raw formula is C27H30O16. So let's go into the Mendeleev table. And most biological molecules will be composed of carbon, hydrogen, oxygen, nitrogen, and maybe sometimes phosphorus and sulfur. So life is chomps, basically. So you can find the mass of the atom, the exact mass. And this is the first important thing, understanding the atomic exact mass. By convention, the exact mass of carbon is 12. But the mass of the other atoms has some decimals somehow. So the hydrogen is 1.007825. And so we need to use these extra digits in the mass to be exact and precise about the mass of the molecule. Consider something, remember that we use the nominal mass and the exact mass. The nominal mass is just the first, it is the unit. It's an approximation at the unit. For example, the nominal mass of the hydrogen atom is 1, but its exact mass is 1.007825. Then also we need to consider that in nature, atoms comes in different isotopes, which can have different natural abundances. So, for example, the carbon is present under mainly two forms, the C12 and C13. The abundance of C12 is 98.93%, and the abundance of C13 is 1.07%. So it means that if you analyze a natural molecule, it will contain one atom of C13 for roughly 100 atoms of C12. Exactly the same for hydrogen. There are different forms that exist. The proton, which is a proton with just one proton and one electron. Deuterium is one proton and one neutron. So it doesn't change the charge system, but it changes the mass. And the tritium contains two neutrons. So the mass are 1, 2, 3 in this case. So these isotopes have different masses because they have different number of neutrons into their structure. So in mass spectrometry, we will separate molecules according to their mass. So what we want to see first, what we're looking for is the monoisotopic mass. So this is what we shall use to measure, to calculate the mass of a molecule. We will take only the mass of the most abundant elements. For example, for carbon, we will use carbon 12 and not carbon 13. If some molecules contain some carbon 13, we will see that during the analysis by mass spectrometry. Remember also that the molar mass, on the contrary, so this is the mass of the product on the package of the product, it takes into account the relative abundance of all isotopes. It's a weighted average of isotopic masses. So in our case with rutin, C27H30O16, we will use the mass of the most abundant isotopes. So the exact monoisotopic mass will be 27 multiplied by 12 plus 30 multiplied by the mass of one proton or of one hydrogen, which is 1.007825, plus 16 times the mass of oxygen, which is 15.99, etc. And so the exact mass with 4 digits is 610 and 1534 atomic mass unit. So AMU. The average mass, taking into account all the isotopes. So the molar mass of this compound in nature would be 610 and 5 to 1 atomic mass unit. So you see there is a difference in the small digits for the average mass and the exact monoisotopic mass. You can find both information on PubChem in the computed physicochemical properties of this compound. And so, for example, here is phytofluene, and in PubChem you can find the molecular weight and the monoisotopic mass of this compound. So how does mass spectrometry works? So it's an apparatus for molecular mass measurement and quantification. So let's play a little game. How can you measure the masses of these cannonballs if you have a cannon and other cannonballs of the same volume but known masses, like 10, 25, and 35 kilograms? So it's easy, in fact. You just have to fire the cannonballs of known masses. So this will calibrate the field of measurement. And so the lighter cannonballs will go farther than the heavier cannonballs. So it means that you have calibrated the field of measurement. And now you can fire the cannonballs of unknown mass, and depending on how far they go, you can deduce, on the scale you've just created, you can deduce their masses. And this is exactly what mass spectrometry does. It's measuring the masses by studying a movement in a calibrated field. And to do so, to move the molecules, you need two separate parts in the machine. First of all, you need to charge the molecules. So you give them a positive or negative charge. And this is done in a part of the machine that is called ionization source. And then you can move these ions into electrostatic fields. And this part is called the mass analyzer. So more precisely, you have this principle here. On the left, the ion source. So you take neutral molecules, the molecules you want to investigate, and you charge them. First of all, this is what is done in the ion source. And once they are charged, you can move them. You can move them basically in a way you want. You can then move them in a straight line, and then in the mass analyzer, you can change their trajectory, and this will give you information about their mass. Usually, the left part, ionization source, can be done at atmospheric pressure when it's coupled with liquid chromatography, and under vacuum when it's coupled with gas chromatography. And in the analyzer, you have a strong vacuum just to avoid that your molecules that are flying there hurt or bump into a gas molecule that would break it. So finally, they will reach the detector. So you got here a little animation on how it works: ionization, acceleration, deflection. First, let's talk about detection. The detection is just giving you the number of ions. It's a quantitative information. The detector doesn't give you any information about the mass or the identity of the molecule. It is just a machine counting the number of ions. So the ions here will bump into a plate, and this plate will generate electrons, that will generate photons, that will generate electrons. And in the end, you have a microcurrent in microvolts, which is proportional to the number of ions that are bumping into the plate. So this is it. This is giving you the intensity of the signal, which is the quantity of the molecules, the quantity of the ions. There are many different types of sources. The most famous are electron impact, which is adapted to gas chromatography mass spectrometry, and electrospray, ESI, which is very well adapted for liquid chromatography mass spectrometry. But others exist, like photoionization or MALDI or LDI or DSI, etc. It all depends on the nature of the sample, if it's gaseous, liquid, or solid, if you have one extraction process or another, and what type of separation process you use, especially gas or liquid chromatography. And then there are the mass analyzers with strange names, like the quadruple, the triple quadruple, the TOF, which is time of fly, or QTOF, which is a quadruple coupled with the time of fly, the Q-traps, the orbitraps, and the Fourier transform mass spectrometer, FT-ICR-MS. When you go down in this list, machines become more expensive and require more expertise to use. But also they have better properties like higher mass resolution. This is something I will talk about a bit later, which is the ability to really measure precisely the mass. Then some of them are able to do MS-MS or MS2 or even MSN, which means that it's possible to break the ion into smaller ions to analyze the structure of the molecule, the structure of this ion. And also they have different detection limits. Some of them have very low detection limit and others have higher detection limit. So it will depend on the abundance of the molecules we investigate. So, in fact, a mass spectrometer is not measuring directly the mass of a molecule, but in fact, it's mass to charge ratio, M/Z, MZ. And fortunately, metabolites are too small to be charged more than once. Usually, there are exceptions. So, practically, Z is equal to 1, and thus we talk about the mass instead of the mass to charge ratio, but technically, this is MZ that is analyzed and not just M. Here is the outcome, the output of mass spectrometric analysis. This is called a mass spectrum. This is a graph with in abscissa, where in abscissa you have the masses, and in ordinate you have the intensity, which is the abundance of these different masses. So here you see different bars in red that represent the different ions that have been found, detected, and their relative abundance. The signal intensity is most of the time indicated as the percentage of the base peak. The base peak is just the most intense ion in the window. If you zoom or unzoom, it can change, the scale can change. Sometimes, rarely, you can have the absolute count of the ions or an arbitrary unit, a microvolt. But most of the time, it's in percentage of the base peak. Now, something important to understand about the measurement of a mass is that it is a statistic process. So it's very fast usually. So a mass spectrum is accumulating a lot of information in 1 second. But it's not perfect. So the signal produced when an ion is detected is a succession of values distributed in a Gaussian way around the true value. This signal is a continuum or profile. So here you have an example with a mass spectrum between 255 and 257, and the mass of the molecule is 256.3, okay? But sometimes the mass spectrum makes a little error, and so it will give you another measurement, something closer to 255.8 or closer to 256.8. And statistically, the mass spectrum will more often give you the good number, a number around 256.3. So this is very important to understand because the ions are reaching the detector continuously. And one molecule gives one ion, but you never have only one molecule. You always have maybe 1 nanomolar of the molecule in your sample. So once you have injected it in the system, maybe you have 1 nanomole, and this 1 nanomole, it's a lot of molecules. And so continuously, over a very short period of time, the measurement of the molecule will occur. And so you see there is a statistical distribution of the measurements. So this signal is called the continuum. And now you can make a small calculus to simplify the information and to access the most precise mass. And you can do that by making a weighted average of the masses measured in the width at half the height of the peak. We call that FWHM, full width at half maximum. So you see, I take the half maximum intensity, and I take every measurement within this section. So these are the green bars. And I make an average. And the average I would get is 256.25. This is the average mass. And what I've just done is to centroid the mass spectrum. I have calculated the centroid value. Often it can be represented like this. Instead of a curve, you have a bar, so a discrete information instead of a continuous information. Another representation, you measure continuum, so continuous data, where peaks are really curves, and you calculate the centroid values, which is more precise, and it also reduces a lot the size of the data. And this is called the centroid spectrum. In the mass spectrum, it's also critical to understand what is an isotopic profile. We saw that in nature, molecules will have different masses depending on the amount of heavy isotopes they contain. So there is 1% of C13 in nature. So in fact, if you have a molecule that is composed only with carbon, one molecule every 100 molecule will have a mass unit, a mass measurement of 1 unit higher, okay? Because it contains one C13 and not only C12 carbons. And so this is what we call the isotopic profile. So if you look at the mass spectrum of a molecule, you will see this typical distribution of the masses, different masses with just one unit between each. And so you have the molecule, so you have a continuum representation on the left and the centroid, which is much more practical to work with on the right. And so you have M, which is a molecule that contains only the most abundant isotopes, H1, C12, N14. But then you have M+1 because these are all the molecules that contain at least one, that contain exactly, one heavy isotope. It can be a C13 or it could be, I don't know, N15 or a deuterium and so on. Well, given the relative abundance, in fact, it's usually C13. And then you have M+2, which are the molecules that contain 2 heavy isotopes, and M+3. And then it's so small that you can find them. So for a molecule, you have a isotopic distribution of different mass peak that correspond to their content in heavy isotopes. Now let's look at ionization sources in more details, and we'll start by the electrospray ion source. We said it already, it's good for liquid samples, it's so useful with razor polar molecules, and it's coupled with liquid chromatography, and we call that a soft ionization. So here is a mass spectrometer, it's an old triple quadruple. And you have syringe pumps that can also introduce the sample into the source, but it can also be connected to a liquid chromatography. And this is the electrospray source here that is shown. It's a block of metal. And inside there is a heated compartment. And outside you have the arrival of the liquid flow. So there is continuous liquid sample flow that get into this block. And you see at the end of the liquid flow device, you have a capillary under high voltage. And all of this is at atmospheric pressure, but it's heated at high temperature. And what is figured in red is the opening that will take the ions made in the source to bring them into the mass analyzer. So let's look at a close-up of this. So you have a continuous liquid sample flow, a capillary under high voltage that will make a spray from this flow, and in a perpendicular way, the opening toward the mass analyzer. And all this at atmospheric pressure. So this is how it works. If there is a constant flow through a capillary, you will have droplets. But if you put a high tension on this capillary, then it makes this particular spray that is quite standard. So these are micro droplets. So we have different parts of it, the cone, the jet, and the plume. And what's happening is in fact that the droplets are charged and they break up in smaller and smaller droplets until you only have charged molecules. So these charged droplets, they explode. We call that a Coulombian explosion because the charges are repulsing each other until you have charged molecules in a gas phase. So this is what's happening in fact. So instead of being from up to down, there it's shown from left to right. But so on the left you have the capillary. Inside the capillary, because of the high charge, it's 2000 volt, for example, 3000 volts. The droplets of the solvent are charged, and so you have these droplets that are going out of the capillary with the famous Taylor cone, and there are so many charges around the droplets that under a drying effect, because we dry the molecule with hot gas in this block. And then the droplet will shrink until there are too many charges and an explosion. And the droplet is divided into two smaller droplets. And the process continues until you have single molecules with charges. And these charged molecules are taken in charge by electrostatic fields that will bring them into the mass analyzer and finally to the detector. So this is another more precise depiction of this. The continuous liquid sample flow at the bottom, 2000 volts on the capillary. And you see a nebulization gas. This is a gas that will help in fact making these droplets. Everything is at high temperature so that the droplets are shrinking because the solvent evaporates. And then the charged molecules are moved toward the mass analyzer, and there is a drying gas, which is also the nitrogen, to avoid that non-charged molecule would be attracted toward the mass analyzer because of a vacuum gradient there is between the source at atmospheric pressure and the mass analyzer, which is under vacuum. Everything that is not going to the mass analyzer is collected into a trash. This process forms quite intact molecular ions. This is why we call them soft ionization. So we start with the molecule M, neutral, And after the electrospray, you will often have what we call molecular ion, which is the molecule plus or minus just one proton, H. So M plus H plus with a mass of M plus 1, and M minus H minus, which is of a mass M minus 1. Unfortunately, there are also many other ions that can be produced from the same molecule. So one molecule gives several ions. We call them adducts, like sodium adducts, M plus Na, or potassium adduct, or ammonium adducts, M plus NH4. And all these ions will have masses that are the mass of the molecule plus the mass of the adduct. And in negative mode, you can have M minus H plus formic acid. Formic acid is an additive that we use in chromatography. So we add it to the solvent to, well, for different reasons I won't talk about here. And then you can have a negatively charged molecule that is with the mass, which is the mass of the molecule plus the mass of HCOH minus the mass of H. So it makes M plus 46. Moreover, you can have fragmentations in source, which means that molecules with hydroxy chemical function can lose a molecule of water. Molecules that are conjugates of sugars can lose the sugar, or conjugate to phenolics can lose the phenols. And this is possible both in positive and negative mode. For example, if a molecule is losing a molecule of water, H2O, during the ionization, it will make M plus H minus H2O, which is M plus 1 minus 18. So the mass of this ion will be M plus 1 minus 18, and so on. So the mass spectrum of one molecule can be quite complex depending on the frequency of these different ion apparition. So hopefully you will find the molecular ion that would be the most abundant, because it is the easiest way to interpret the mass spectrum, and also because it's easier to break down into smaller pieces if you want to make to make a structural analysis. But most of the time, you will also find other adducts that you don't really want. In fact, sometimes they are useful to make a diagnosis and to be sure of what is the mass of the molecule, but most of the time it's not really desirable. So here are the most common electrospray ions, both in positive and negative mode. So in positive mode, of course, M plus H plus, which is MIM. So MIM is the monoisotopic mass, plus 1. Sometimes there is a dimerization. The molecule makes a dimer before being ionized, so you have 2M plus H. So it will be twice the monoisotopic mass plus the mass of a proton, 1. M plus Na, M plus K, M plus NH4, M plus H minus H2O, and sometimes the loss of 2 molecules of waters, M plus H minus 2 H2O. In negative mode, the most common ions are M minus H minus, which is a monoisotopic mass minus 1, M minus H plus HCOH, this formic acid adduct, and M plus Cl minus. So this time, this is a negative ion that is added to the molecule, a chlorine, and so you have the monoisotopic mass plus 35, which is the mass of this atom. Here is an example with the 8-hydroxygeranial. This is a very common compound you find in many fragrances, and it's made by many flowers. It is also a basic compound, or it is close to very basic compounds that are participating to the terpene metabolism. So its mass, its monoisotopic mass, is 168.23 atomic mass unit. And here is the mass spectrum obtained in positive mode. You can see its positive mode on the top right of the graph of the mass spectrum. You see scan ES+. And so you see that this molecule, we injected the pure molecule, and it makes a lot of ions. 123, 150.9, 191, And we don't find the M plus H. The M plus H would be 169.23. But it's not apparent here. Instead, we have 123. What is it? Well, in fact, it corresponds to the fragmentation, the in-source fragmentation of this compound. That is losing both a CO, that is a carbonyl function, and a water molecule. So it gains one proton, but it loses these two chemical functions. So it's 168 plus 1 minus 28 minus 18. And then you can also explain the mass 150.9. Well, it's a low resolution mass spectrometer here, so you can round it up to 151. And this is the loss of a molecule of water. So this time it has just gained a proton and lost H2O. And also 191, which is the adduct of sodium, M plus 23. There is one big problem with the electrospray source, which is called ion suppression or ion enhancement. The ionization of a molecule in electrospray and thus the intensity of the signal depends on many factors. Of course, the abundance of the molecule, that's obvious, but also the source parameters, the voltages, the temperatures, the flow, the source geometry. So from one analysis to another, if you don't use exactly the same parameters or even exactly the same machine, you can have slight variations of the abundance of the different ions. It will also depend on the chromatographic parameters, the solvents, the additive, do you have formic acid or not, for example. And also from the environment of the molecule during nebulization, in particular the presence of molecules competing for electric charges, like phospholipids. So if your molecule is eluting after separation, at the same time as another molecule that can take the charges, then you will have what we call a matrix effect or a high ion suppression or enhancement effect. The problem, of course, is that the matrix effect depends of each molecule in the sample. So you never know if a variation comes from the abundance, a different abundance of the molecule, or if it comes from just the presence of another molecule that creates ion suppression. You have here an example. You have the same concentration of a molecule, but one of them is diluted in water, in solvent, and the other is diluted in a complex sample that contains many other compounds. And you see that the signal obtained, so this is a chromatogram signal here. So you have the retention time in abscissa and the intensity of the signal in ordinates. You have the analyte in the sample and the analyte in the standard with the pure solvent. Well, the signal is suppressed in the sample because of the presence of other compounds. In this case, these are phospholipids. And if you remove phospholipids before the analysis, you will gain a lot of signal from the molecule, despite the fact they have the same concentration before and after. So it's quite difficult to check this because you have to make this type of experiment to check if there is or not a matrix effect. And so you will add the molecule at different concentration, either in pure solvent or in matrix. And you will make a calibration curve with each of these set of reference. And if the calibration curves are parallel, it means that you don't have any matrix effect. But if the calibration curves are not parallel, then it means that depending on the concentration of the other molecule in the matrix, it will change the signal of the molecule under investigation. So in this case, you know you have a problem because there is a matrix effect, and you will have to be very cautious for any determination. And maybe you will have to make internal standardization with stable isotope labeled pure reference compounds to take into account this matrix effect and to correct it for a good quantification. Let's see now the electron impact source. It's electron impact, sorry, not impact electron. It's EI. It's designed for gaseous samples, and so for rather non-polar molecules or polar ones, but after derivatization. It's very suitable for GC-MS analysis, and it's what we call a strong ionization. So here is how it works. You have your GC with the oven, inside the oven a capillary column, and the injector on one hand on the left, and the column connected to a transfer line toward the mass spectrometer on the other side. And in between you have the electron impact source, which is under strong vacuum. So this is how it works. So this source is just a block of metal with a filament that is subjected to a certain tension, 70 electron volts, and it will emit electrons. This filament will bomb the molecules that come out of the capillary column in gas phase. Under vacuum, it will bomb them with electrons, and doing so, it will ionize them. It will charge them positively by, in fact, stealing electrons from the molecules. And these charged molecules are sent to the mass analyzer. All this is also at high temperature to avoid a recondensation of the molecules. So it works the following way. The electron at high energy, 70 electron volt, will steal an electron from the molecule, and it will make a radical cation, M plus dot. And this is very unstable, so the molecule will explode because of its internal tensions, and you will have in-source fragmentation, a lot of it, in fact, and you will have many ions that are just M plus, resulting from this ionization process. This is why we call it a strong ionization, because it makes a lot of fragment in source. So the electron impact spectra are complex, but they are also very reproducible, and they are quite unique for each compound. So it's very interesting because there is a lot of databases that allow to identify a molecule just on the base of its mass spectrum, because it is so reproducible and so unique for each compound. So here is the mass spectrum in electron impact of linalol. Linalol is a compound that is quite close to the hydroxygeranyl we saw previously. It's the same type of molecule, but you see that in electron impact, you have many more fragments. You have dozens of them, in fact. And so this is what I just said. And you have at 154 the molecular ion M+. You see that this fragment, this ion is very small. It's not abundant at all. And what you will find very abundant are fragment pieces of this molecule. After the sources, let's see how works the mass analyzers. Let's start with a simple one, the quadrupole. It's made of 4 electrodes in parallel that will create, when submitted to a current, an electrostatic field. So this is the little sketch on the right. And in this electric field, if you send ions between the electrodes, in the tube, in fact, they will adopt a trajectory in a spiral. And this is what this little movie is intended to show you. So this is a quadrupole, and this is the trajectory of the packs of ions, and depending on their mass to charge ratio, some of them won't make it to the detector, while some of them will be detected. So this is the principle. This electrostatic field in this particular device will select a particular mass to charge ion. So basically it acts as a filter for the ions. So this is another representation. You have your quadrupole, a detector, and the ions coming continuously from the source. At time t1, there is a particular set of tensions in the electrodes, which is U over V. I won't get into too many details there. It's a radio frequency signal. Well, anyway, and the pack of ions enter the tube of the quadrupole, and only some of them will make it to the end, while the other will be lost on the quadrupole itself. So in this case, only the blue ion is making it to the detector, and it will be detected and generate a mass spectrum for the ion that was selected at this time, which here, for the sake of clarity, is supposed to be of a MZ ratio of 100. The intensity of the signal is proportional to the quantity of these ions that reach the detector. Here I only figure 1, but of course you have packs of ions. Don't forget that here I tried to decompose a mechanism that is continuous. The ions from the source are coming continuously. And here we're talking about very, very short intervals of times. Then a little while after, well, a few seconds after, or milliseconds after, time t2, there is another tension that has been set up on the quadrupole, and then the same packs of ion coming continuously from the source. Well, some of them will pass, others not. This time, the only one that can pass is 101. Okay, so this is a green ion here. And the mass spectrum is building itself like this over a few milliseconds. The time that the range of masses you wanted to explore has been scanned. And so on. So the cycle of the tension variation is called a scan. When it's finished, it goes back to the first tension, which means it will scan again the ion 100, and then 101, 102, etc. But it's not really like this. I make it a discrete mechanism while it's a continuous mechanism. It goes continuously, and the variations of the tensions are continuous. So the scan time is the period necessary to filter sequentially all the ions in a defined mass window, like, for example, from 100 to 1,000. This is very typical for this type of machines. And the quadrupole operates at very high speed. It's not the fastest mass spectrometer available, but it's already quite fast. And so a scan time is very short. It's a few dozens or dozens of milliseconds. When a scan is over, a mass spectrum is generated and a new scan cycle begins. And so every scan is characterized by the production of a mass spectrometer. Okay, so first, the scan mode of this quadrupole. This is what we just saw. So you have a cycle between, let's say, 100 and 500 of a mass to charge ratio. The ions are coming from the source, and they will cross the tube of the mass analyzer and reach the detector. So sequentially, first 100 and then other masses, until you make a full mass spectrum. And when it's finished, it will start over again. And so every scan, you produce a mass spectrum. Now there is a second way to use a quadrupole, which is the SIR mode, single ion recording, or sometimes you find single ion monitoring, SIM. In this case, the quadrupole is set to a particular MZ ratio. Let's say here 355, because you know that the molecule you want to analyze, you want to quantify, has exactly this mass, 355. Remember, Quadrupoles are low-resolution machines, so you don't need many digits after the unit. So you will have a nominal mass of 355. So this time, only the ion with this specified mass to charge ratio will be filtered through and reach the detector. So the packs of ions come from the source in a few milliseconds, but every time this is only 355 that can go through. And in the end, you get one mass spectrum, but this is the mass spectrum of 355. So the interest of this mode is that you can focus on one particular compound, and it's very cleaner. It's much cleaner than the scan because you filter many ions. They never reach the detector, and so you have a filtration of the noise, and so there is less noise in this mode than in full scan mode. Let's see now the second type of most common mass analyzer, which is the time of flight, TOF. This time it's a high-resolution mass spectrometer. And you see it's a tube, it's a metallic tube in which the ions will fly, in fact. And this is the time it will take for them to reach the detector that will indicate their mass-to-charge ratio, MZ. So it's not scanning, it's not filtering, it's very fast and very resolutive. We say it's high-resolution mass spectrometry, HRMS. So this is the principle. Here you have this draft. So you have ionization source, and then you have a starting grid, which is a pusher, an electromagnetic pusher that will push the ion through the tube. And at the end of the tube, you have what we call a reflectron. So this is another pusher, and it will send the ion in the opposite direction. The idea is to double the time of flight, so the precision on the time will be more accurate. And finally, in the end, you have a detector that will count the ions. And at the bottom left, I show you the kind of mass spectrum it will give. So from the ionization source, you have these packs of ions coming continuously, and then they are pushed. And depending on their mass-to-charge ratio, they will take more or less time to cross the tube. The heavier the mass, the ion, the more time it will take. And this is what is measured here. We measure the time between the first pusher and the detector. And for each type of ion, it will give us the MZ ratio. And when it's finished, it goes again to a new cycle of push and fly and detection. So the ion masses are deducted from their speed in the tube. Now let's talk about another type of mass spectrometer that is very important, which are tandem mass spectrometers. In this case, we don't use just one mass analyzer, but several. And the first case is the triple quadruple that we call also TQ or 3Q. In this case, 3 quadrupoles are arranged in series, quad 1, quad 2, and quad 3, between the ion source on the left and the detector on the right. So first, let's analyze a scan mode. You can do exactly the same operation that you do with a single quadrupole that we already saw. So if you want to scan between 100 and 500, you will have 2 passive quadrupoles and 1 active quadrupole. And you will get exactly the same result with a mass spectrum of the ions. Now, the single ion recording mode works also exactly in the same way. Quad 1 and 2 are passive. They let every ion pass. And the third quad will filter out everything but 355. But now, and this is what matters with this type of machines, you can make what we call a daughter scan, DGS. It's a scan of the fragments of a particular ion. This is what we call also MSMS or MS2. MS2 because it's a 2-dimension mass spectrometry. You first analyze the molecules and then you fragment them and analyze the fragments. And this is very important to give you information about the structure of the molecule, and it's also very important to identify the molecules. So in this case, the second quadrupole will be a collision cell. this is a part in which the molecule will be fragmented. So we have two mass analyzers, quad 1 and quad 3, and one dissociation cell or fragmentation cell. So to make a daughter scan analysis, first the quad number 1 on the left will be in single ion recording mode. Let's say you want to analyze the fragment of this ion of mass to charge 355. We call him the parent ion. So it's a selection of this particular ion. Okay, only this ion goes into the dissociation cell. And there, several things will happen. There is argon injected. It's an inert gas, so it's not going to change the ionization, but we add also some electric shocks, what we call a collision energy, and that will make the ion to interact, to bump into the argon atoms that are in gas phase. And this will break the ion into many fragments, some of them being charged. And these ions are called the daughter ions. Okay? So in French, we call them les ions fils. Well, so, and in English, it is the daughter ions from this particular parent ion. And then the third quad will be scanning between 10 maybe and 355 to scan all the daughter ions from this parent. Okay? And so you have cycles. At every cycle, the same 355 is selected, but then the third quad is scanning, and so you make an acquisition of the daughters of this parent ion. And what you get in the end is the daughter mass spectrum of the parent ion 355. And so you see the masses of the different fragments of this molecule. Now there is another mode, which is called the MRM mode, multiple reaction monitoring. In that case, it means that you already know what are the daughter's ion of your parent ion. And what you want to do is you want to isolate this compound in a mixture, and you want to quantify only him. So to do so, you will make a double filtering, a filtering on the first quad, then you break this parent ion, and a filtering on one ion, on one daughter ion, which is a fragment of this parent ion. So in this case, imagine you select the 355, but problem, you have two molecules which are different but have the same nominal mass, 355. You break them in the second quad. They will give their own daughter ion that might be different because they don't have the same developed structures, okay? And then the third quad will be also filtering one particular daughter, a daughter that is specific to the molecule you want to analyze. And so this is what's happening. You generate a mass spectrum of the daughter ion of a particular parent ion. So this is how we write it, 355 greater than 151, the parent and the daughter. It's very interesting also because in this case, the method is quite selective. Even if you have isomers with exactly the same nominal mass or exactly the same mass, maybe in one of them you have a different ion. And so you can choose this ion to separate with the mass these two isomers and to quantify only the isomer of interest. It's also nice because for quantification, there is a double filtering of ions. So in the end, very few ions reach the detector. And so the noise, the background noise is minimal. And so it's a very interesting technique to quantify traces like phytohormones or very low trace pollutants. And of course, at each time of the cycle, the same operation is repeated and you obtain every time the same mass spectrum. So remember, double mass filtering, parent and daughter, it is the most specific mode of a triple quadrupole, and you have very low noise to signal ratio, so very low limit of detection, LOD. It's widely used for targeted or multi-targeted quantitative analysis. Now let's have a look at a particular method development for MRM. First, you will make a scan to determine the parent ion. Here is a case of loganic acid of monoisotopic mass 376.3. It's a pure compound, and you analyze it with LCMS, triple quad. And here is the mass spectrum of the full scan of this compound. So you see many ions. You see M plus H plus, but it's not the most abundant ion. You also have an adduct of ammonium, M plus NH4 plus. But the most intense is a fragment, is an in-source fragment of loganic acid, and it's 215. So you will choose this as a parent ion. And now you will make a daughter scan to see all the parents of this parent ion 215. And you will select the most abundant fragment, the most abundant daughter ion, 108.9. And so you have developed your MRM method. It is the parent ion 215 giving the daughter ion 108.9. Now you can make an MRM analysis of this compound, and this is what you get. You will get a single bar because you only see this particular signal. 215 gives 108.9. So to summarize, scanning is good because you can explore a large mass range. It is the most comprehensive sample description. The problem is you have a very complex signal and very high background because many undesirable low trace ions will be there to make noise. Then the single ion recording, it's interesting because it's quite specific. It's not very often used in itself. It's used to develop an MRM method. Then the daughter scan will give you structural information. It's an MS-MS information. You've got information about the fragments produced by a molecule, by an ion. And it's also useful to develop an MRM method. And then the MRM for targeting targeted analysis with quite high specificity. And this is a method of choice for quantitative analysis. It's got a quite low limit of detection. And so this is why most people buy a triple quadruple. It's to make MRM analysis. Now it's possible to have another type of tandem mass spectrometer. We saw a triple quadruple, but it's also possible to use a quadruple, a collision cell, and a time of fly. And it's quite interesting because the time of fly is high resolution. It will give you the masses of the daughter ions with a high resolution. And it's very important, in fact, to determine the raw formula of this ion. And this can give you very important information for structural analysis. So you have ion source on the left, then the quadruple to select a parent if you want, and then the collision cell to dissociate this parent, and then the TOF that will analyze with high resolution the daughter ions. So of course, all this device is maintained at low pressure, so under high vacuum. In this case, the TOF here you see it makes a kind of W trajectory because you have several reflectrons that are meant to increase the separation of the ions based on their mass, and so this is why you can reach high resolution. So this is how it works: the ion source, the first quad, second quad, and then the high resolution MS, the TOF, time of flight, and finally the detector. So first you can use an MS mode. So it means you want to see the ions that are present in a mixture. So the first quad is passive, the second, the dissociation cell, is passive, and the TOF will be active. And so your ions will reach the TOF, they will be pushed, and then depending on their time of fly, you will generate a high resolution mass spectrum. So you see it's a high resolution because you have a precision of several digits after the unit. Now with the QTOF you can also do MS-MS or MS2, some daughter scans. So this time you select one parent, maybe 402.3, with the first quad, you dissociate it in the collision cell, and you analyze the daughters with high resolution with the TOF. okay? And what you generate is a daughter scan mass spectrum with high resolution on the measurement of the fragments, both, in fact, the fragments and both the parent. And finally, you have MEC mode. In this case, the quad 1 will be either passive or active depending on the timing. So it will switch between passive and active mode. Same stuff for the second quad, the dissociation cells. So first stage, you have a simple scan of the parent ions. And then the second part of the cycle, the collision cell will be active and will dissociate all these ions, and you will have all the daughters of all these ions. And so you do that, you alternate MS and MS2 mode, and so you have a profile, a chromatogram of the parents and a chromatogram of the daughters. So, well, the only problem is to be able to associate correctly the daughters to the correct parent. And you can do that with retention times. The parent and its daughters have exactly the same retention times. So this is important to have a good separation before this analysis to correctly assign the daughter to a parent. And I'm sorry, I said I made a mistake. The first quad remained passive anyway, because the idea is to see all the daughters of all the parents. The last configuration for mass spectrometers, mass analyzers, are the orbital trap or orbit trap. It is the most recent design, and it's very powerful because it will measure with very high resolution. And so this is this type of device. You see, it is a block with a little space in it, and within this space you have an axis made in metal as well. And this axis is an electrode, and the borders, the walls of the block are also electrodes. So this is how it works. The ions will enter this trap, and they will orbit around the axis, the axial electrode. And depending on their orbit, they will induce a current that will be deciphered by a Fourier transform mathematical process to isolate each frequency of each ion, each type of ion, each ion of a given mass to charge ratio. Remember, this is what we want to measure. And this will be translated into a mass spectrum with high resolution. So I don't want to go into too much detail for this, but the idea is that it's a very efficient mass spectrometer, which is almost as sensitive as a triple quadruple, but with a high resolution of a time-of-flight machine, and even more, in fact. So this is a setup with an orbit trap. You have also a collision cell. You can have a quadruple to select a parent, and of course an ion source. And you see that you will guide the ions from the right to the left, and you will make a high-resolution orbit trap analysis of in scan mode, in single ion mode, or in MSMS mode without any problem. So LC QTOF and LC orbit trap, so mass spectrometers hyphenated to liquid chromatography, are very commonly used for untargeted analysis. So what most people think is really metabolomics. Now just a word about the analytical performances in terms of precision and accuracy. If you look at a mass spectrum from far, let's say, you will see these little sticks, vertical sticks. But if you zoom in, maybe you will see a bush of peaks, in fact. Remember that before making centroid transformation, the signal is continuum. And so it means that you have curves there. And if you zoom in, you can see maybe a very good separation of different masses. So this is the case, of course, only with high-resolution mass spectrometers. Now, precision and accuracy are two very important notions of metrology. Metrology is the science of measurement. And so it's not only for mass spectrometers, but it's true for any kind of analysis. So the precision that we will assimilate to the resolution here is the spread of the values when the same ion is measured several times. So it's a standard deviation. It is the spread of the measurement. It depends on the intrinsic performance of this machine. The accuracy or exactitude in French is the difference between the exact calculated mass of an ion and the mass effectively measured. It depends on the quality of the apparatus calibration mostly. And the values are often expressed in ppm, part per million. So the little sketch on the left can show you what it means. So precise and accurate. So on the top left, you have not precise, not accurate measurement. The average value is very far from the true value, which is the center of the target. This is the actual mass, the calculated mass. And the dots are very, very spread with a high standard deviation, because when you repeat the measurement, you have a completely different measure. On the top right, you have a precise but not accurate measurement. When you repeat the measurement, then the dots are quite clustered and you have a smaller standard deviation. But when you average this, well, the mass is completely different from the actual mass of the compound. On the bottom left, it's not precise, but it's accurate. If you repeat the measurement, the standard deviation is high, but if you average this, you will be pretty close to the true value that you expect. And then, of course, on the bottom right, it's precise and accurate, and this is what you look for. Another way to show that, well, this would be a peak of mass, exactly as I showed you when we talked about continuum and centroid data. This is a peak, and the precision, well, it's the width of the peak. Sometimes we use the width at half-8. The accuracy is the spread between the peak, the top of the peak, which is the average measured mass, and the actual true mass that is shown by the red stick. Now, the resolution is the ability of the mass analyzer to distinguish two very close masses. So in practice, it depends on the width of the mass peak. Two ions with very close mass are generally considered resolved if the valley is below the mid-8. So on the left part, you have resolved peak because the bottom of the valley, the bottom of the valley is below half the 8 of the most intense peak. But on the right, it's not resolved because the valley is above this half 8 of the most intense peak. So in the first case, you can say you have separated the two compounds by the mass. On the right, in the case of the right drawing, it's not possible to say you have separated these two masses. So R can be easily quantified. In fact, it's a ratio. It's a ratio between the actual mass and the smallest mass difference that can be discriminated, which is usually measured at half-8 of the mass peak. So this is what you have shown here. So you have the width at half-8 of the peak, delta M, and M, which is the mass. And so R is a very big number, a figure. It's usually above 1,000, and it can reach up to millions, in fact, when you have very, very high resolutions. And it reflects, of course, the device's ability to distinguish close mass over charge molecules. We call them isobars. Isomers are molecules with exactly the same raw formula and thus exactly the same mass. Isobars are molecules with the same nominal mass, but they are sufficiently different so that they don't have the same exact mass. Here you have the case of two molecules. One has an exact mass of 230 0.0069, and the other has a mass of 230.0134. And so they have the same nominal mass, which is 230, but they have different exact masses. So they are isobars and not isomers. And you see here, if you have a machine with a resolution of 25,000, which is quite high already, you absolutely cannot discriminate these two compounds. If you have a resolution of 35,000, you can begin to see that there are two molecules, in fact, in the same mass peak. And if you increase up to 65,000 the resolution, then you can clearly separate these two compounds. The accuracy will be the exact mass minus the measured mass divided by the exact mass. So it could be a percentage. It would be a percentage of accuracy. But it is so small that we express it in part per million. So we multiply this by 1,000,000 and we express it in part per million. These analytical performances are very important to identify compounds because exact mass measurement, which depends both on precision and accuracy, will give you very few raw formula possible. And raw formula, which is the elemental composition of the molecule, is extremely important to start identifying this molecule. So here you have an example with a quadrupole and a time of flight. One has a precision, an accuracy of 368 ppm, and the other of only 1 ppm. And you see that the raw formula that can be calculated with the first precision of the quadrupole, there are many of them. You have more than 4,000 compounds, raw formulas that could match this particular precision, but accuracy. Sorry, but with only 1 ppm of accuracy, then you only have 11 raw formula that can match this accuracy. So here are some ranges of resolutions and accuracy. For a quad, the resolution is a few thousands, and the accuracy is above 3 ppm or even more. For time of flight, the resolution can reach 40,000 or 50,000, and the accuracy nowadays is more between 1 and 3 ppm. The Orbitrap has a resolution of 100,000 and an accuracy below 1 ppm. And the Fourier transform mass spectrometer have a resolution of 1 million and an accuracy that is below 0.1 and 0.5 ppm, so much higher resolution and accuracy. One last piece of information about the analytical performances. It is the instrument dose response curve. Any instrument, so of course mass spectrometers, show this type of dose response curve. It's a S curve. This is a black curve here. So in abscess you have the concentration or the dose of the molecule you want to analyze. And in abscess you have the intensity of the signal. In ordinate you have the intensity of the signal. And so at the beginning you're just at the level of noise. The noise is the minimum signal. You can't go below that. It is due to permanent contaminations and also just the electronic noise. The simple fact that there is a measurement of a tension in microvolts means that you will have always electrons passing there and you will have a minimum signal. This is noise. Then the signal increases when the concentration increases, and you reach the limit of detection. Usually it's 3 times the level of the noise, but you can also measure it empirically. And then you have the limit of quantification, and the limit of quantification is the bottom of the linear part of the curve, and usually it is assimilated to 10 times the noise. Then you have a linear range, so you increase the concentration and the signal increases proportionally. And the slope of this curve is, of course, the proportional factor, and you call it the sensitivity. And finally, you will reach the up part of the curve where the signal will flatten. You can increase concentration, but it won't much increase the signal until it doesn't increase the signal at all. And then you've reached the detector saturation. You can increase the concentration as much as you want. You won't gain any signal. The detector is already saturated. What we call the dynamic range is the concentration at which you have between a signal giving noise or detector saturation. And most importantly, you have the linear dynamic range. And this is the part where you can make quantification. And so this is only between during the linear range of the slope, the curve, sorry. Here is an example of this linearity for a triple quadruple with a linear dynamic range of 10,000. It means that the apparatus will give a proportional signal in a range of concentration between 1 and 10,000. Now, the fourth chapter is about data analysis. There would be a lot of things to say about that, but we will only see overlook what is really important and what are the different problems regarding data analysis that you might want to overcome. The first step is to track errors in the data set and to correct it for the many biases that is unavoidable today. The factors of variation between samples are first the effect of the control variables. So treatments, genotypes, this is what we are looking for. We are looking for the effect of these control variables in the experiment. We want to know what change in metabolism after the treatment, or what differences a mutation induced in the metabolism. But there are also a bunch of other variations that are not quite as interesting. For example, the biological variation between experimental replicates. Every plant is unique unless you work with clones, and even in this case, there might always be some marginal variations. Like for Arabidopsis, which is a model plant, they are homozygous, so they should be all the same, but we observe that some of them will grow faster and others than others, and so on. So even for a given genotype, you can have variations. So that's the first main source of variation, and this is why we have to replicate the experiment. We have to take several samples, in fact, as many as possible. The absolute low limit is 3, because with 3 you can calculate an average and a standard deviation, which is, well, somehow consistent. But, well, in many cases, statistics will be very efficient if you have 30 replicates. Well, in this case, it's obviously not easy experimentally, because you need space and it's a lot of more work, and so, well, it's not always possible. Then you have experimental and expected variations like temperature gradient, light gradient, border effects. These can be managed if you are aware of those gradients. If you work in a phytotron, then you know that the light, you can map the light on the plateau where you put your plants, and you can make rotation of the plants so that they receive the same amount, globally the same amount of light. If you're in a field, you know that there is a border effect, and so it's very common practice to let the first meter of the borders in the field and not to collect them, because they will have undesired effects from the simple fact they are at the border of the experimental field. Then you have experimental errors, like during sampling, when you crush the samples, when you weight them, during the extraction, the conservation, the injection. The list is very long of everything that can go wrong within this experiment. So it requires some expertise and know-how. You need to do that several times before you really know what can be the problems at these different steps. So we prefer experienced technicians to do these steps, and they can be very harmful to the results. And finally, there are systematic errors or random errors related to the equipment. The pipettes, when you pipette a volume, the injector syringe, the MS sources, in which things can go pretty weird sometimes. So all these sorts of variations are not desired. So we need a way to somehow limit them. First solution to reduce the bias is to practice a good experimentation. So choose an appropriate biological material. Take into account the experimental gradients. Make the effort to find them and to correct them. Make regular calibrations of measuring equipments. Train the people who are going to work on the machine and apply cleaning procedures that are suitable for this type of work. Then one basic rule is to always inject blank samples. These blank samples are just empty vials that are treated exactly as if they were a sample. So when you do a sample extraction and before the analysis, and you have to weight some biological material, you will add some solvent, you will make a process of extraction and heat and agitate and so on and centrifuge. And in the end, you will have a clean extract ready to inject in the machine. Well, the idea is to do exactly the same with one or several blank, which will follow exactly the same step, but the only difference is they do not contain any biological material. And they will track any contamination. Everything you find in the blank comes from a contaminated solvent, a contamination in the any of the equipment that you've used to prepare your sample. So you have really to do this to find the background noise of your experiment. What is a metabolite and what is not. This is an example with the chromatogram. The up chromatogram is a sample and down the chromatogram is a blank. And you see that you have many peaks in the sample and some of them are not present in the blank. So they are metabolites. These are the peaks you want to focus on. But there are also other peaks that you find both in the sample and in the blank. And they are contaminants. You don't want to spend time with this, or you may want to investigate where they come from. In this case, the two first contaminants are in fact derivatization agents remaining after the preparation of the samples. You may also detect cross-contamination with this. So if you inject many samples, you can contaminate your machine. And this contamination will provoke a problem for the subsequent samples you inject. So here, for example, you inject a pure reference standard, which is quite concentrated. And then you inject a blank just after that. And you find a trace of this same molecule. So it means that the preceding injection has contaminated the following injection. The problem is, if it's a blank, okay, you can detect that. But if it's another sample, maybe you will be unaware of this problem. So this is why it's very important to check every 10 samples injected to check that the blank is still blank and you don't have these cross-contaminations. These problems can be difficult to solve sometimes. Another very important thing is to use, whenever possible, internal standards. So the internal standard is a molecule that is not native from the samples. You don't find them naturally in the samples, but you will add them to the extract in the same amount in every sample. Ideally, you will introduce them as soon as possible upstream in the extraction or preparation of the sample process. So usually we introduce it with the extraction solvent. So the solvent contains a certain concentration of internal standard, and since you put the same volume of solvent in every sample, you will have the same amount of internal standard. And then every sample follows the same process, And in the end, the internal standard will track and will tell you if there's been any problem with a particular sample. If you see a strong decrease of the internal standard in one sample, you can say, okay, maybe something went wrong, and maybe we've lost some sample. Maybe the tube got open at one point, and we've lost a bit of the liquid. Or maybe the molecules have been degraded because maybe this sample was not stored properly, and so on and so on. So this will tell you if all your sample followed exactly the same process, and if you can you can then identify technical problems. Whenever you have variation of the internal standard, and even if this variation is small, you can correct your signal by just normalizing by the signal of the internal standard. So here, for example, you have 3 chromatograms corresponding to 3 samples, sample 1, 2, and 3. And the blue curve is the signal of the internal standard. Normally, there should be the same signal in every sample. But this is not the case. In sample 1, the internal standard is very low, while in sample 3, it's very high. And then you have the molecule of interest. It's a green curve. So here we detect, thanks to the internal standard, that there's been a problem somewhere. Something went wrong. And so we can correct the green curve by taking into account the blue curve. So what you will do basically is you will increase the signal of sample 1 and decrease the signal of sample 3 so that the 3 chromatograms display the same signal for the internal standard. And you do that, of course, homogeneously within a chromatogram for all the peaks. So you make the hypothesis that all the molecules, and especially the molecule of interest, have been submitted to the same problems that you detect with the internal standard. So in practice, it's very easy. You just have to divide the surface of the peak of interest by the surface of the internal standard. So you make your integration to quantify these peaks, and then you just make a ratio, and you will have a normalization of your molecule of interest by the internal standard. So this is what is given after internal standard correction, and on the bottom right, that was before. So before, you might have concluded that the sample 1 contains less of the green molecule than the sample 2. But if you correct by the internal standard, you see that this difference is not obvious at all. And it will also reinforce the difference with the third sample, in which the peak has been reduced due to the internal standardization. So this will give you, hopefully, a better quantification of, or relative quantification of all the molecules of interest. To have a good internal standard, it must not be native of the sample to be assayed, be structurally and physico-chemically close to the molecule to be assayed, be analyzable with the apparatus used, and it mustn't coelute with the molecule to be assayed and or produce a signal indistinct from them. You must be able to integrate it correctly. In mass spectrometry, we only use internal standards in targeted approach. This is something we can't use in non-targeted approach for some reasons I will develop later. And we use other techniques to correct the signal, and especially the drift of the signal during the batch of analysis. So it's a snitch, it's a spy that will allow to detect suspicious samples, correct undesirable microvariations, and well, it's very commonly used in GCMS, but not in LCMS, as we said, because of the properties of the electrode resource. Another very important thing to do is to use a QC sample, or quality control, or a pool. We can distinguish the pool and the quality control. So first, the pool of a powder is very interesting, as we said, to make different extractions, to work on the chromatography, on the MS parameters, to develop analytical methods. But you can also make a pool of the extract by taking the same amount of every sample of your experiment, pull it, so it's a fraction of it, of course, maybe 10 microliter over 1 milliliter. And then you will have a pool of all your extracts that you will use to control the signal drift during analysis. So this signal drift is a big problem. It's linked to the fouling of the electrospray source. Some parts, and especially the cone that leads to the mass analyzer, will get dirtier and dirtier when you inject dozens and dozens of samples. And because of this, the signal will decrease non-linearly according to time. So this is what you have here in the left part of the slide. You have the number of injection, the rank of the injection, and the signal intensity, let's say, for the same molecule. And so you start with a very high signal because your source is very clean at the beginning. And then it goes dirty and the signal decreases. And it doesn't decrease linearly, so you will inject several times QC until the signal stabilizes. Of course, you will lose some limit of detection or some sensitivity for the method. But on the other hand, you will have a stable signal for the next dozens of samples injected. So this is the solution number one. You cause deliberately fouling to dirty the source by injecting many times the quality control, this mixture of all your samples. The second solution is to inject regularly, and one is not exclusive of the other, is to inject regularly, maybe every 10 or 15 samples, you re-inject the QC, so the same sample again and again. And then you will use a software or an algorithm that will analyze the drift of the signal for this for each peak of the QC and correct it along the batch of analysis, the run. And it will correct in the same way all the other peaks in all the other samples. So you use the quality control to make a correction, to find a linear, or it's not a linear, it's a polynomial regression, to correct every peak individually and to do this in every sample. So this will erase a lot of these undesired variations linked to the modification of the source. Some experiments generate a very high number of samples. This is very true in metabolomics. And so you will inject your compounds in batches, and maybe you will clean the source in between. And so by doing this, you will completely change the response of the source. And it will modify the signal baseline. So there again, you can use the quality control to correct the signal in order to have the same, in order to be able to compare your sample from one batch to another. In regard to this, it's also a good option to smartly prepare your sample list and the order in which you will inject your samples. The goal is to dissociate unwanted sources of variation from the source of variation in the study. So it means that you will dissociate the biological replicates from one another, and you will not inject at the same time all the replicates of one particular experimental modality. So this is here you have a list of sample, the rank of injection. So the bad process, you see, you have, of course, you have blank. You inject many times QC to follow the source. You inject blanks again to be sure that you don't have unwanted contamination and so on. And then you inject all the first modality, the 3 replicates of wild-type control, and then the 3 replicates of wild-type stress, and then the 3 replicates of mutant control, and then of mutant stress. If you have a gradient of change in the response of the machine, it's very bad, because the difference between mutant stress and wild-type control might be due to the fact that one is a mutant under stress and the other is a wild-type under control condition. So that would be the control variables. So it might be due to that, but on top of this, you can add an unwanted variation that is due to the fact that the mutant stress were injected much later than the wild-type control. And so your machine has changed, the source has been dirty, and so you will have false positive. You will conclude of difference, or you will have false negative because it depends on the sense of the orientation of the variation. A good way to do is to separate your replicates, and within each replicates use a random disposition. And in between every replicates, inject a QC so that you can correct the drift of the machine. So you see, there is also, and this is very important, in fact, it's a major source of error, and it's something that is bothering everyone because you need to make a statistical correction, and it's much better if you maximize the variance between replicates, because then it won't impact the variance that is due to your control variables. If you need to use calibration curves for targeted analysis, for example, you want to analyze caffeic acid, and so you have a calibration curve, you might want also to inject several times this calibration curve, because you might be surprised to see that the signal will change during the course of the analysis. So then also you will have to correct this drift to properly integrate the peaks and quantify this compound correctly. Let's have a look now at the raw data treatment. The raw data are basically chromatograms and mass spectrum. So when you make a mass spectrometry analysis, this is what gives you, this is what the machine gives you first. So you can explore them manually. And this is what is a MS chromatogram. First, you have the axis is time, and the ordinates is the intensity of the signal. And you have peaks that correspond to ions that have been detected, each ion coming from hopefully one molecule. It's a 2D signal, 2 dimensions. So you have retention time and intensity. As you can see, it's not a totally continuous curve. In fact, these are several points that you link together, so you have something, somehow a curve. But if you zoom well enough, you see it's not a curve. It's a succession of points, of measurements. And the duration in time between, so the duration between 2 points is the time the machine needed to make a scan, or to make an MRM or a SEER. Anything that you ask it to do, it takes a certain time, and when it's finished, then it will acquire the following point, and so on and so on and so on. So it is the time for the machine to generate a mass spectrum. Okay, so this is what has been produced during this very short lapse of time. It's a mass spectrum. You can use a third dimension to make this mass, to put this mass spectrum in the same graph. So you will have another dimension, the Z axis, that will be mass over charge, mz. And you have this for each time point. So in fact, what you really have is a 3-dimension data: retention time, intensity, and mass to charge ratio. So this is what it looks like. Retention time, masses, intensity. And analyzing a data set is playing basically with these 3 dimensions to know if you can or not compare signals from different samples. If you take slices of these 3D data by mass, then you have chromatograms. For example, if I look only at the mass 603, then I have a chromatogram and I see a peak wherever there is an increase in the signal of this particular mass 603. If I take a slice of this data, a perpendicular slice at a given retention time, what I see is the mass to charge ratio, which is a mass spectrum. Okay, so it's very important to understand how these two interact, and in fact that they are part of the same data set. But these are 2 representations: chromatogram for a given mass, or a sum of different mass, and mass spectrum. The mass spectrum, the different masses at a given retention time. The first information the machine will give you is the total ion current. In fact, this is the sum of all the ions detected, and the intensity, so is the sum at each time point of all the ions detected, total ion current. You see here we have 3 molecules, the molecule 2 and 3 being only partially separated. If you right-click on the computer, at the top of a peak, you will see the mass spectrum at this particular retention time, which is mostly the mass spectrum of the molecule, but also a bit of background. Now you can decompose the mass spectrum by projecting on the third dimension and exploring, in fact, the mass spectrum of the different molecules altogether. For example, if you click on the mass 101, you see that this ion is made by the first molecule, so it is present in its mass spectrum. It is not in the mass spectrum of the second molecule, but it is also in the mass spectrum of the third molecule. While the ion 195 is made by all three molecules. What we do here is we're looking for extracted ion chromatograms. These are chromatograms of a given ion in the complex mass spectrum of a given molecule. And what we've done is a deconvolution, and this is very important. A deconvolution is the fact, the operation to look at all the ion. We can name XYCIC or EIC, extracted ion chromatogram, in all the chromatograms. So you're making a list, a full list of the ions in the whole data set, in all the samples. And then you will align these ions. That is, you will determine the couples, the pairs, retention time ions that represent the same molecule in all samples. It may sound trivial to do that, but it's very difficult to have an efficient algorithm to do that, because you have small variations in retention time and small variation in the measurement of the masses. So you have to define basically what belongs to the same molecule. And it's not that easy, and even the best algorithm might do some errors sometimes. But nowadays, we find algorithms that can do that quite well. Then you will reconstitute a deconvoluted spectrum for each molecule, taking into account only the ions that belong to that molecule. So the different software, you have the Chromatoph for GCMS from the brand Leco, Progenesis from the brand Waters, Target Links, which is more for targeted analysis, XCMS, it's an air package for non-targeted GCMS or LCMS, and you have online solutions like Workflow for Metabolomics, where you can upload GCMS or LCMS data, play with a few parameters, and let the servers calculate and align your sample to extract your biomarkers. It works quite well. It's not perfect ever. The non-targeted deconvolution, well, this is what is difficult. Well, you will have to automatically find peaks in the chromatogram. So assigning a signal to the same ion, I already said that, this is the alignment, and gathering these ions to finally have your markers. So this is the workflow that is followed by the algorithm XCMS. So it's a several package on the R program, and you have here all the steps for this deconvolution. I'm not going into the detail of this because it would take 20 hours to really make you understand what it is and how it works in detail. But well, it's not the purpose of this course because we don't have any practice. But you see, it's quite a universe you have to go to go into, and you have to read all the information about what is doing the algorithm to be able to choose the right parameters depending on your data set. So this is how it ends in a script, and the blue part of the script are the parameters you can change. You see there are many parameters you can play with, and depending on the parameters you will have different results. So really it takes a lot of time to master these tools, and you have to play with them quite frequently, otherwise you will forget how it works and you won't be able to do that anymore. Well, in the end, obviously, hopefully, you have the result of a deconvolution, which is a data matrix. It's a huge table where you have in rows the individuals and in columns the variables. And at the cross-section of individuals and variables, you have peak area. So this is the quantity of this particular peak for this particular individual.